All right, I'm back with another super brief video on the next topic that we're reviewing, which is circular motion and gravity. So if we start with circular motion, pretty much anything that goes in a circle, the reason why it's going in a circle is because there's a centripetal force on it. Centripetal force, not centrifugal. We'll talk about that real quick in a second, not that. So the idea is, let's say this object, when you look down from above, is going clockwise. The velocity is always going to be what we call tangent or tangential. So no matter if you're there, if you're here, if you're at this point right here, you're at this point here, remember your velocity is always tangential. And at the same time, your velocity is tangent. The force that's on this moving object is always perpendicular to it. And that perpendicular force is what makes it change direction. So it doesn't change the speed. Remember, velocity is a vector, so it has it's speed plus direction, essentially. The speed doesn't have to change, but if the direction changes, then the velocity is changing. And this force that's perpendicular always points to the center because the center is always perpendicular to tangent. So this is always going to point to the center, this is going to point to the center, and this is point to the center. So we call that center force the centripetal force. And in fact, it's really just the net force that's acting on it. And if we call that net force the centripetal force, then the acceleration that goes along with it is called the centripetal acceleration. Now, how do we calculate the centripetal acceleration? We just call it A sub c. It's that tangential velocity or speed squared divided by the radius, and that's the distance from the center of the motion to the outside of the circle there. So that explains sort of some of the calculations that we're going to do. That's the centripetal acceleration. The centripetal force is just going to be m times that, so we just put mv squared over r. Okay, some other calculations that we might do, and this is going to be a review from a math class for you. If you go around a circle, the distance around that, the distance around this circle has a special name. It's called the circumference, and it's equal to 2 pi r or pi d. And the time it takes to go around once is given a special name. That's called the period. So if you figure the distance around is the circumference and the time it takes to go around is the period, the speed is just the distance divided by the time, or in this special case for circular motion, it's 2 pi r divided by t. Okay, so those are our three formulas for centripetal force and centripetal motion. Okay, the next topic that goes along with circular motion, and sometimes I write it as UCM, which means uniform circular motion. That just means when V is constant, which is kind of a necessity for what we're doing. The other thing that we do at the same time is universal gravitation. And the reason why we put these two together is because gravity oftentimes is the centripetal force. If you remember from what I just erased there, the net force that's pointing to the center is known as our centripetal force. There's a bunch of different ways to get a net force to the center. You could have, a rope with a mass on it, and then in that case, tension would be the net force to the center, or would help to provide the net force to the center. If you're a satellite or a planet in motion, then gravity is what provides the centripetal force. And this is why we're going to talk about universal gravitation. If you're a car going around a turn, friction would provide the centripetal force. If you're on a roller coaster, it might be the normal force, right? Your seat is what's holding you into that circular motion when you go around the loop-de-loop. Okay. Again, anything that points to the center is a centripetal force. But when we talk about universal gravitation, basically it's one big equation here. This is F sub g. I shouldn't write it this big. Let's make it really small because it's not F times g. It's just the force of gravitation is known as the gravitational constant times one mass times another mass divided by r squared. So what that means is if I have one mass here and one mass here, separated by some distance r, there's some force of attraction. We normally don't notice it because these masses are small, but if one of these masses is Earth, then it gives rise to a big enough force that you actually feel it. And that F sub g we can write, when we know the gravitational field strength, we can write it as m times g, where g is equal to 9.8 meters per second squared, or newtons per kilogram is the unit for that. Right. So some things to learn or to know about this. We can obviously, use m times g when we know g. So if you're on Earth's surface, sure, just do that. Or say you want to know what's the gravitational field strength on Mars. If you knew the weight of something on Mars and you know the mass of something, then you would just divide and that would tell you what little g is. Important to note, mass never changes. Okay? You go from one g field to another, Earth to the moon, to Mars. I don't even know what Mars is. Let's say it's 3 meters per second squared. That g can change, right? But the m can never change. So your kilograms stay the same. So don't ever think that just because, what if I go to the moon? What happens to my mass? Nothing happens to your mass. This formula here, it has a special well, it's not special, but it's known as an inverse square relationship. So that means the force of gravity is proportional. That's the symbol for proportional to 1 over r squared. What that means is if I want to know how strong that force is, and this probably is kind of obvious, the further I get away, right, the higher my r, or more this separation is, the less the force is. Now, some people might think that it does that. It doesn't. That's not an inverse relationship. This is an inverse relationship. Okay, so just make sure you're... All right, I'm trying to keep this under 10 minutes, so the last thing that I'm going to do here is a really simple one. If you have some mass here, and this again could be something like Earth, if you wanted to draw the field lines, and we just got done doing this with magnetism, gravitational field lines are super simple. Pretty much anytime you put a mass anywhere outside of the thing that's causing the field lines, it's always an attractive force. So this is what the field lines look like for gravitational field lines. They're just always pointing towards the center of the other object. 8 minutes, not bad.